Hi to whoever is listening into this presentation. My name is Mohammad Taha and I'm from IIT Delhi. I'm excited to present my work on optimization of beamwidth on automotive radars based on statistics of street geometry. This work is a part of my PhD, and I hope it will provide insights into improving automotive radar performance in urban and suburban environments. Let's dive into the content. In this presentation, I'll cover the following key points. Introduction will give a brief overview of the problem and its significance. In the motivation, we'll see why this research is crucial for modern vehicular applications. Then we'll look at the network geometry, how we model the streets and vehicles using a spatial stochastic process. Then we will dive into the statistical analysis and quantify the radar performance through detection success probability. We will then look at the numerical results and finally the conclusions and the future directions. To lay groundwork on our discussion, let's start with the basics of line process. A line process is essentially a collection of random lines in a 2D plane whose location and orientation in a representation space forms a spatial stochastic process. To put this into perspective, when you sample a random variable, you get a number. Similarly, when you sample a spatial stochastic process, or in this case, a line process, you get a realization where there are random number of lines having random locations and orientation. The figure here shows a realization of such a process. These processes find application in diverse areas from in urban infrastructure planning to wireless communications. On this slide, we see the representation space of the line process. Representation space are used to map the parameters of the line process. Now, each line is uniquely characterized by these two parameters. It's the perpendicular distance r from the origin and the angle theta formed by the perpendicular line and the x-axis. This figure illustrates how first a point is generated in the representation space with r and theta uniformly distributed, then mapped onto the Euclidean plane. In our case, we take the binomial line process whose representational space or the generating set is a finite cylinder. Each line corresponds to a point of a binomial point process generated in this generating set. Unlike the Poisson line process where the generating set is an infinite cylinder, here we consider this line to be generated in a finite area, but then these lines extend up to infinity. Following figure illustrates the generating set and its mapping in the Euclidean plane. As you can see, the lines are mapped onto a confined circle, and then these lines extend up to infinity. In binomial line process, the number of lines or the generating points are fixed in B, and the location of these points are uniformly distributed. Now, to better understand the binomial line process, let's compare it with the classical Poisson line process. Firstly, the binomial line process has fixed number of lines, while in case of Poisson line process, the number of lines are Poisson distributed. Importantly, a key distinguishing feature of binomial line process is its inhomogeneity. Unlike the Poisson line process, which is homogeneous, the binomial line process exhibits spatial variability in the density of lines. This property makes it more realistic for modeling urban and suburban areas. This comparison highlights why the binomial line process is better suited for capturing the structure of real-world road systems where the street density varies significantly across different regions. And this brings us to our first motivation. One of the key motivations for this work is the inhomogeneity of urban and suburban regions. City centers typically have higher streets and vehicle densities, while suburbans are less dense. The variability is often overlooked in classical models like Poisson line process, Poisson-Voronoi tessellations, and many more. The figure here shows the built-up area of Borodо city, illustrating how street density changes across different parts of the city. The red part has been modeled by a higher intensity based Poisson-Voronoi tessellation, but as you move out, the intensity used to model these lines is decreasing. So instead of using a multi-intensity based Poisson-Voronoi tessellation, we want to capture this inhomogeneity using binomial line process. Now, how to capture this inhomogeneity mathematically? We derive the line length density of binomial line process. So for a binomial line process generated with NB lines, the line length density at a distance r from the origin is given by rho r. We see that for small r less than rg, the line length density is relatively uniform, reflecting the high concentration of streets in urban cores. But as R is greater than Rg, the line length density decreases, mirroring the sparse street networks in urban or rural areas. The second aspect, the second motivational aspect of my work is uh, we see that the radars are essential for advanced driver assistance system, supporting features like adaptive cruise control, obstacle detection, and many other applications. However, as the number of vehicles equipped with radar grow, mutual interference becomes a significant issue. Current models often assume simplistic highway scenarios or uniform distribution of vehicles, which do not reflect the complexity of real-world environments. So our work aims to bridge this gap by incorporating street geometry into radar performance analysis. So far, we have discussed the concepts of line process and understood the binomial line process as a powerful tool to model real-world street systems. Moving forward, we will now delve into the practical implication of these models by first looking at the network of uh, automotive radar networks. The streets in our network are modeled as a non-homogeneous binomial line process having NB lines or streets and are generated inside a circle of radius RG. Vehicles are distributed along these streets. To model this, we distribute random points on each line of binomial line process having intensity lambda. This results in what is known as a Cox process. So the complete distribution of vehicles forms a non-homogeneous binomial line Cox process. This process captures the spatial distributions of vehicles in a way that reflects the structure of real-world road systems. Uh, our analysis focuses on an automotive radar mounted on a typical vehicle, which we term as ego radar. The ego radar can be located on any street, but because of isotropic nature of binomial line Cox process, we assume that the ego radar is on line L naught, that is the y-axis at location 0, R naught. Also, let the half power of beamwidth be omega, and the target is at a distance r. The following figure here shows realization of this automotive radar network modeled using the binomial line Cox process, where the ego radar is located on street L naught at location 0, R naught. The distance to the target is r. The blue points represent the non-interfering radars, and the red points representing the interfering radars. So not all the radars, not all the vehicles equipped with radar can cause interference. So this figure here illustrates which of these radars can cause interference and which of them cannot. We see that the ego vehicle A experiences interference only from vehicle B. Now, if the ego vehicle is at location E, the vehicle E experiences interference only from vehicle F. From this illustration, we see that the interference occurs only when both the ego and the interfering radar enter each other's beam simultaneously. Here we represent the set of interfering automotive radars at the location of ego radar as phi bi. Now, how do we mathematically characterize this? I'm not going to into detail. This brings us finally, the third aspect of this modeling is signal to interference ratio. The signal to interference ratio at an ego radar is expressed in this equation. The S is the reflected signal power received by the ego radar from the target vehicle. The omega c is the radar fluctuating cross section, which is modeled as an exponential random variable. And the interfering signal received by the ego radar undergoes multipath fading, modeled as a Rayleigh fading, and is given by this parameter I, by this expression variable I. This brings us to our first metric to characterize the performance of an ego radar in a binomial line Cox process modeled network, which is the detection success probability. We define the detection success probability as the SIR distribution. That's the probability that a signal to interference ratio is greater than a certain threshold beta. The theorem here gives us the detection success probability of an ego radar where the location of vehicles is modeled as BLCP. There are two parts to this expression. The red part of the expression highlights the effect on the detection probability due to interferers present on the ego radar street, that is L naught. The blue part of the expression highlights the effect on detection probability due to interferers present on the intersecting streets, which are NB minus 1. For more nuanced part of the expression, please refer back to the paper. Now, this is how the detection success probability looks like with respect to two important parameters, R0, which is the location of the EO radar in the city, and the beam width. Figure A illustrates the detection probability of EO radar at different locations within the city as the vehicle moves from the outskirts, that's R0 is equal to minus 10,000, to the city center, that is R0 is equal to 0, and then back to the outskirts, that is R0 is equal to 10,000. Here's what we observe. As the ego radar moves towards the city center, the detection probability initially decreases. It then saturates to a certain level, then within the city center. Finally, as the vehicle leaves the city, the detection probability again increases. This behavior can be explained by the anisotropic nature of the radar sector. Although the street geometry is isotropic, the radar sector is not. Thus, the detection probability seen by the EO radar at R0 is equal to plus 10,000 is not same as R0 is equal to minus 10,000. We also observe that the saturation region of the detection probability depends upon the beam width omega. For smaller values of omega, the saturation region is larger. For larger values of omega, the saturation region shrinks. Finally, we will see finally the second figure shows the impact of beam width on detection probability. Figure shows the plot of PDV as a function of half power beam width omega for different values of R0 and the intensity of vehicles. The key observations include that as omega increases, the detection probability decreases nonlinearly. At the city center, the impact of omega on detection performance is more pronounced compared to locations farther away. For lower beam width values, the street containing the ego radar contributes significantly more to the interference than any other street. Consequently, the detection probability is nearly the same for initial values of omega, regardless of R0. Regardless of R0. Now, from the cognitive radar's perspective, now this brings us to our second metric, second parameter, which will help us optimize the beam width, which is the average number of BLCP points in the radar sector, or essentially the potential number of targets seen by the ego radar in a radar, So this is a critical parameter because it directly helps us estimate the number of successful detections by ego radar. Then this NBR gives the average number of BLCP points in a radar sector is found by taking the product of intensity of vehicles on the road, lambda, with the expected length of lines falling within the radar sector. To calculate the average length of lines present inside a radar sector, we calculate the line length density, which we had earlier seen over the region of the radar sector. While I won't get into the equation here, the figure illustrates how this calculation varies depending upon the location of the ego radar. The figure highlights 3 cases out of 5 cases, where in the first case, the ego radar sector is lying completely inside the city. In the second case, it's lying partially inside and outside. And in the fourth case, it's lying completely outside. This brings us to our second metric, which is the number of successful detections. So this is one of the key outcomes of our analysis, where we find a lower bound on the average number of successful target detections, denoted as NDB. This lower bound reflects our focus solely on targets within the ranges less than R. The lower bound provides a reliable estimate for system designers, allowing them to optimize radar parameters such as beam width and distance to the target R to maximize detection performance. How can we do that? Is if you can by looking at this figure. Figure shows the plot of number of successful detections with respect to beam width. From this plot, we observe an important trend. Initially, as the beam width increases, more target falls into the radar's detection sector, leading to an increased number of successful detections. However, beyond a certain point, the probability of successful detections decreases due to the increased interference caused by the wider beam. This creates a trade-off between the detection probability and the number of targets that can be detected, resulting in an initial upward trend followed by a decline in ND. Thus, there exists an optimal beam width denoted as omega star, which maximizes the number of successful detections. From a cognitive radar's perspective, optimal beam width should dynamically adjust as the ego vehicle moves from one side of the city to another city. Uh, yeah. Now these plots here highlight the optimal beam width with respect to R0, that's the location of the ego radar in a city, and the distance to the target R. Figure A, we plot the optimum beam width versus R0 for different values of NB and intensity of vehicles. Here we observe an interesting trend. As the R0 increases, the optimal beam width first increases, it then saturates in a given region, then it again decreases. This behavior might seem counterintuitive at first glance. One might logically assume that optimal beam width should be higher outside the city compared to within the city limits, given the sparser street networks. However, we observe the opposite trend. At the outskirts of the city, having a larger beam width does not significantly increase the potential number of targets related to the detection probability. As a result, smaller values of omega prove optimal. Likewise, we see the behavior of optimal beam width with respect to distance to the target R. For ego radar located outside the city center, the beam width must dynamically decrease as R increases. In contrast, for R naught is equal to 0, that's near the city center, the optimal beam width saturates for some initial values of R. As R increases further, the rate of interference rises sharply to smaller values of omega star. Eventually, the optimal beam width saturates again for larger values of R. But these findings underscore the importance of adaptively adjusting the radar beam width based on the either vehicle's location and the target's distance. This is some more results where we see that how the detection probability looks like with respect to distance of target R and lambda. As expected, if your distance to the target increases or more vehicles come onto the road, detection probability decreases. In conclusion, the binomial line process presents a novel way to model the real-world road systems. By utilizing the binomial line Cox process for automotive radar networks, we enabled a detailed examination of interference characteristics leading to significant insights. Our findings highlight a notable trade-off between the radar beam width and number of successful detections. These outcomes hold promise for applications such as collision avoidance, lane keeping assistance, and pedestrian identification. The further work may include target tracking and an ISAC modeled binomial line Cox process for network optimization. Now, this brings to the end of this presentation. Thank you all for your attention.